All right, welcome to The Explainer. Today we are tackling one of the absolute biggest, most brain-melting ideas in all of physics, Einstein's special relativity. It's a theory that completely tore up the rulebook on space, time, and, well, reality itself.
So let's just jump right in with a question that sounds kind of obvious, right? Is time the same for everyone? Of course it is. A minute for me is a minute for you. But what if I told you the universe doesn't see it that way? That right now, your clock is ticking just a little bit differently than the clock of someone flying in a jet plane. To figure out how that's even possible, we need to take a step back and look at how we used to think about the world.
You see, for hundreds of years, physics felt, well, easy. It made sense. Thanks to guys like Isaac Newton, we had this common sense view of the universe. Everything just worked the way you'd expect it to. The rules were simple, and they matched what we saw every single day.
And the main rule, you could call it Galilean relativity, was super simple. Speeds just add up. That's it. And look, it works perfectly for pretty much everything in our day-to-day lives. You know, throwing a ball, walking on a bus, it just makes intuitive sense.
I mean, think about it. You're on a train, it's chugging along at 50 miles per hour. You throw a baseball forward at 10 miles per hour. To someone just standing on the platform watching you go by, how fast is that ball moving? 60, right? 50 plus 10, easy, obvious. For a long time, we thought this was just how the universe worked, period.
But then, something weird happened. In the 1800s, scientists were digging into electricity and magnetism, a totally different field, and they found something that didn't play by the rules. It was like a crack started to form in that perfect, common-sense picture of the universe. And that crack was light. So this guy, James Clerk Maxwell, comes up with these incredible equations, and they predict that light is a wave. Okay, cool. But they also said it travels at one specific, constant speed. We call it c. And the truly bizarre part, it wasn't constant relative to anything. It was just constant for everyone, always, no matter what. And that, well, that was a massive problem.
Okay, let's go back to that train. But this time, forget the baseball. Imagine you're on a super fast rocket ship moving at, say, 99% the speed of light. You turn on a flashlight and point it forward. Now, common sense says the light beam should be moving at the speed of light plus the speed of your rocket, right? But Maxwell's math said, nope, it's still just moving at the speed of light, c. You see the problem? Both of those things can't be true at the same time. Something had to be wrong.
So scientists at the time were like, okay, wait a minute. Maybe there's a simple explanation. Sound travels through air, right? Waves travel through water. So maybe light travels through something too. Some kind of invisible cosmic jello that fills up all of space? They called it the luminiferous ether. And if this ether was real, then as the Earth moves through it, we should be able to feel a sort of ether wind.
And that's exactly what two scientists, Michelson and Morley, set out to measure. They built this brilliant device. The basic idea was to split a beam of light, send the two new beams on a race in different directions, and then bring them back together. The thinking was, if there's an ether wind, one of the beams should be a tiny bit slower than the other. It would be a super small difference, but their machine was sensitive enough to catch it.
So they run the experiment, and what do they find? Absolutely nothing. Zero. No difference between the beams. No ether wind. They thought, maybe we're just lined up wrong. So they rotated the whole thing. Still nothing. They tried again and again for years, making it more and more precise. The result was always the same, a big fat nothing.
This was a disaster. The one experiment that was supposed to prove the ether existed and save common sense physics totally failed. And what that meant was physics was broken. The whole thing. Either the simple speeds add up rule was wrong, or our entire understanding of light was wrong. The very foundation of physics had a massive crack running right through it.
And then along comes this young guy working in a patent office in Switzerland, Albert Einstein. And in 1905, he just blows the whole thing wide open. He didn't try to fix the old ideas. He said, let's just throw them out and start over. And he did it with just two really simple but really powerful new rules.
Okay, so rule number one was this. The laws of physics are the same for everybody. Doesn't matter if you're standing still or flying through space in a rocket ship, as long as you're not accelerating, the rules don't change. There's no special center of the universe perspective. Everyone's view is equally valid.
And his second rule? This is where it gets really wild. He took that big, annoying problem, the constant speed of light, and he just made it a rule. He said, that's not a problem, that's a law of nature.
The speed of light is the same for every single person in the universe, no matter how fast they're moving. Period. End of story.
Now, those two rules sound pretty simple on their own, right? But here's the thing. If you accept that both of them are true, then reality itself has to get weird. Really weird. Our entire common sense idea of how the world works just breaks down. Think about it. Speed is just distance divided by time, right? So if the speed part, the speed of light, is always the same for everyone, but people are moving at different speeds relative to each other, then something else has to change to make the math work. And Einstein's brilliant insight was that the things that change are space and time. For someone moving really fast, time literally slows down and space literally shrinks in the direction they're moving.
I know. That sounds completely insane, like something out of a movie. But it's real. We can actually measure it. And one of the best ways we've proven it is with these tiny little particles called muons. They're basically raining down on us all the time, created way up in the atmosphere when cosmic rays smash into it.
So here's the mystery. These muons, they don't live very long. At all. Like 2.2 microseconds. That's 2.2 times millionths of a second. Even though they're zipping along at almost the speed of light, with that short a lifespan, they should only make it about 600 meters before they just disappear. But we find them down here, on the ground, after they've traveled thousands and thousands of meters. So how is that possible?
The answer? It's exactly what Einstein predicted, time dilation. From our point of view, standing here on Earth, because that muon is moving so incredibly fast, its little internal clock is ticking way, way slower than ours. So what's a couple of microseconds for the muon is a much longer time for us. Plenty of time for it to make the journey down to us. And look at the numbers. It's not a small effect. It's the difference between seeing almost none of them and seeing millions.
Okay, but let's flip it around. What does the muon see? From its perspective, its life is totally normal. Its clock is fine. It only lives for 2.2 microseconds, so how in the world does it reach the ground? Well, from the muon's point of view, it's not time that changes, it's space. The entire distance from the upper atmosphere down to the ground gets squished, it gets shorter. The journey is just not as far for the muon.
And this is the real kicker. Who's right, us or the muon? The answer is both. Both perspectives are 100% correct. For us, it's time slowed down. For it, the distance shrank. Reality isn't this one fixed thing. Time and space aren't just this empty background. They're part of a single, bendy, stretchy fabric called space-time, and how you experience it depends entirely on how you're moving through it.
So when you boil it all down by just taking two simple ideas and following them to their logical conclusion, Einstein totally flipped our understanding of the universe on its head. He showed us that the world we see, our common sense reality, it's just an illusion, a side effect of the fact that we move so slowly. And it all started with just one little contradiction about the speed of light. It really makes you wonder, right? What else about our reality isn't quite what it seems?